All right, we started out our circuits class, I think in the first class even, or maybe the second class last semester, talking about conservation of power. Before we even really introduced the concept of resistance, we were talking about conservation of power. Well, we have to conserve power in AC circuits just the same as we did in DC circuits. So now, however, we have a little bit more complicated expression for power, right? We know that there's real and reactive parts. So when we're talking about conservation of AC power, if power is flowing in to our circuit, all of that power is going to be consumed, right, in the circuit. And so the complex real and reactive powers of those sources have to equal the respective sums. And this is just addition of complex numbers, right? The real parts add and the imaginary parts add. So it's really nothing, all that different. And so here we see an example of the parallel connection. If I want to know, okay, here's a voltage supply, it's pushing some total current into my circuit. What current goes through I1 and I2 through the respective Z1 and Z2 loads, right? I can figure that out by saying, okay, I know that the complex power, again, here we have a bar to represent the complex, or it's like a vector. And so we have V times I star, right? Which, by Kirchhoff's current law, I1 and I2 sum together to give me I. So I can substitute those in, right? And then I can distribute the V times I1 star, V times I2 star, and I get the complex power in Z1 and the complex power in Z2, right? So the sum of the powers in the two individual elements equals, of course, the sum of the total power. Now, that intuitively probably just makes sense, right? But again, this is a nice way of thinking about, okay, if I'm dealing now with these complex numbers, how do I approach, doing something like current division, right? This is essentially what this current division has just happened, right? And we've derived it, if you will, in a way from power. So the series, the same thing applies, right? There's a same current flowing in each of these, so we can look at the total power, and we can say, well, it's the sum of the voltage drops, V1 and V2, distribute the I, and you can say, oh yes, the total power coming into my circuit from the source equals the total power dissipated in my two resistors individually. And again, we did these in like chapter 1 or chapter 2 of the book as well.